Hello. Hey guys.
Hi, good morning, Professor.
Good morning. Good morning. Happy to be here with you guys.
Yeah, so right now we have 100 students joined, and we open these to all the departments and all the universities, including
Awesome.
Colombo, Moratuwa, and everywhere. So we hope like many people will join. Today is a holiday in Sri Lanka. So in next week, we have more participants than this, I hope. So we can start the meeting right now, like
Mhm.
seminar. I will hand it over to Niumi. So basically, Niumi will give a brief introduction, and later on we can start straight away.
Sounds good. Awesome.
Okay,
And
Niumi,
thanks
over.
thanks to everyone for coming on a holiday. It's great. The team of the committed is often what I'll say. The folks that are here are likely to be the folks that are are going to succeed. So yeah, sounds good.
Okay, Niumi, over to you.
Okay, thank you, sir. Hello, everyone. Welcome. As you know, we are in a world that moves fast. The computers don't just follow commands, but create, innovate, and even dream. This is exactly the scope and potential of generative AI that pushes the boundaries of what's possible. So, if you want to learn about the novel technology of generative AI, you are in the right place. So, I welcome you all to the embark of a lecture series on building generative AI applications. To guide us in this journey, let me introduce the well-known individual who is an honorary professor at the Department of Electrical Engineering at University of Moratuwa and also a professor of computer science at University of Michigan and also the president of Jaseki Labs and the co-founder of Mica.ai and many more that contributes to the field of generative AI. So a warm welcome to Professor Jason Mas. As the Electrical Engineering Society and the department, we are truly honored to have you here with us in this journey. So with that, let me hand over the session to Professor Jason Mas to inspire us with your expertise. Over to you, sir.
Awesome. Awesome. Thanks so much. Thanks so much. Absolute pleasure to be here. Let me share my screen and get set up here, and then we'll jump right in. Um, let's see. All right, let's get the sharing going. Let's see. Let's see. Hmm. I've got too many screens up. All right, here we go. All right. So you guys can see that?
Yes, yes.
Awesome. All right. So folks, like feel free to use the chat to ask questions. I'm happy to answer questions throughout. And then also feel free to speak up. This is it's an open forum. So if you have anything that you'd really like to ask as we go on this journey, yeah, don't hesitate. So okay, so wonderful introductions. You guys probably know about me and the journey that we've been on. I'm very excited. Been working for a long time with folks in Sri Lanka. Logi has been a great connective tissue to all of the good work that's been going on, and we have a growing group of phenomenal talent in Sri Lanka that's on the journey of creating the kind of AI possibilities and the kind of AI technologies that I believe will define how we build products and experiences in the future. So, yeah, so today I wanted to do two things, right? So we're going to talk a little bit about, I'll talk a little bit about the journey, this particular seminar, and what we aim to achieve. So ultimately, what we're going to do is This is really going to be a seminar where we're going to cover both the concepts and some of the theoretical underpinnings that has created the AI revolution that we're in right now. And we'll also build, and we're going to be practitioners. There's going to be a project. We're going to have groups, and I'm after this particular session today to kick things off, Logi's going to share with me all of your emails, and we'll create a group online using Piazza where you guys can connect and participate and engage and ask questions asynchronously, right, offline. So that's coming up. But in the beginning, what I'm going to do, like today, I'm going to talk a little bit about what AI is, and then we're going to be looking at some of the absolute cutting edge papers and future sessions that really define what's coming next. And then we're going to be practitioners in creating that landscape, that next. Yeah, anyway, so that's really the arc. But today, let's start with what really AI is. I would be remiss in my duty of running this seminar. It's such a broad audience. There's so many skill sets and talents. I have to make sure that you leave this class with an understanding of really this is so mysterious, right? We have all this Gen AI and all this good stuff, this Chat GPT. We love it. But what are these models made of? And then I'll talk briefly on what's on the horizon that will be part of the kinds of projects that we're going to go on a journey to create in the scope of this seminar. But first I always show this slide just so we understand how our world works, right? And so this is the top market cap companies in the world. And this is essentially, a company is almost like a country where it has a currency. There's a notion of a GDP, a gross domestic product. Companies' market capitalization is kind of like aggregate GDP, right? It's how much of our world economy is consumed by that currency. So Microsoft stock is a currency, and Apple is a currency, and NVIDIA is a currency. And one thing we'll observe is that unlike, say, 50 years ago, where there were no tech, no AI, no software that was dominating the world, it was primarily oil and energy and healthcare and financial institutions that dominated the top market cap companies in the world. But now it's software, it's technology, it's AI. All of the companies that are here, NVIDIA, Apple, Microsoft, Alphabet, Amazon, Meta, even TSMC, because TSMC actually builds all of the chips that NVIDIA releases. So every GPU you use was fabricated at a company called TSMC, and that's in Taiwan. And so they're one of the world's top 10 biggest companies at the tune of $724 billion. Microsoft is at $3 trillion. And Microsoft is a software company. They don't really do hardware. They have a cloud business, but they're not competing with Amazon. Amazon has a bigger cloud business. Microsoft is software. And this leads to a very, very important point. At this point in the economy, and thank you for sharing your emails. Like that's wonderful. Logi is going to reach out and collect all of those, and then we're going to get you guys into the online system. So thanks for that. But one thing about software, and this is a very special time in world history. It's a super special time in world history because software is the great global equalizer. Software is the first class of product that it disrupts economic systems, right? So often products were physical things, and you had the notion of the bourgeoisie and the proletariat, right? You have the labor the labor folks and the owner class, the labor class and the owner class, right? Where the means of production, owning the means of production made people really, really rich. And then a lot of folks, the folks that worked in the factory, so the means of production would be the factory, the folks working in the factory really had an upper bound as to how wealthy they can be, right? And when you're making physical products, you need to have a factory, and then you need to have people work in that factory. And then the worker and the owner is two distinct things. The owner doesn't work in the factory, and the revenue or the money you make is a product of how many widgets you can build. The owner class would hire others to build the widgets, and then they would just reap the benefits of the scale of using other people's time. And that was essentially how products worked before there was software. Now, things are different. When you build a piece of software, when you put work in to creating something, you can benefit. You are the owner class because you can benefit from scale, digital scale, which is copy. We can copy those bytes and then sell it, right? And so you can be both the owner and the worker and scale to any level of wealth. And this applies to anyone with an internet connection and a computer. We have access to all of the knowledge, and even easier now that we have generative AI, and we can create, and then we can sell and distribute without having to have that distinction between the owner class and the labor class. What that means is any Joe Schmo with an idea and the wherewithal can create something special. And any Joe Schmo can get that special thing in the App Store, or they can get that special thing in the, Amazon's store, right? Like everyone has a store, and getting your app on that store is not that hard. And if your app is special, then you can get rich. And so here's an example. Spotify. I like to use Spotify because it's not from the Valley. It's not from, what we're used to, right? Like, Elon Musk, right? This is from Sweden, an unlikely place when it launched. And the creators of Spotify were just two IT people. They ran a ISP, right? Internet service provider. And they had an idea, man, wouldn't it be great to have a great piece of software that could be the central place for music? And so they started Spotify. And Spotify now, as you know, is a multi-billion-dollar company. And that's a special thing. It happened in an unlikely place. It wasn't in the US. It wasn't in the Silicon Valley. It was in a place on the globe. And there's many, many of these examples, right? Spotify, of course, the market cap is $28 billion. So that means that with an idea and persistence and the wherewithal, you can participate as in the global economy in a new way. And software has created this for us, right? So I want us to really keep that in mind and understand that this is what is allowing a new class of opportunity and success that's available really to anyone that has a computer and the internet. That's all you need to invent, create, and scale impact in the world. Today, that's the new world we're in, actually. It's crazy, right? So let's keep that in mind. Anyway, in our mission, in our seminar, and we're going to coordinate this asynchronously through Piazza, and we'll likely have a Discord that people can log on to communicate. We're going to be forming, so start thinking about organizing yourselves into groups of 3 to 4 people. There's going to be paper readings and paper presentations that'll be presented by you guys, and we'll talk more about that in our next session. And there's also going to be a project after that series of paper where I'll work directly with teams to help them build something phenomenal and build something ultimately that in principle could be taken to to launch on that global marketplace, right? So I look forward to mentoring groups that are really enthused and motivated to go on that journey. So, oh, and there'll be prizes too. We'll describe. So the top projects there's gonna be 3 prizes with like, well, actually prizes that carry value, let's say, and these prizes will be distributed to the most successful projects. Anyway, okay, so that's a little bit about the course. That's a little bit about the perspective that's part of the journey that we're going to go on. Let's jump in and understand models. What is a model, right? So everyone's heard of AI, right? And AI can mean many things. We all know that deep learning used to be deep learning. Before there was ChatGPT, there was incredible hype about deep learning. And that was a phase where it was really the scientists and the practitioners that were talking about AI, like in a sophisticated way. And we've come to a point now that we've had what I call the iPhone moment, right? We've had the moment where this idea that we were working on captivated the world in a fascinating way. And now the world is all honed in, focused on that as a table stakes way of life for how we move forward, right? It's a lot like the internet, you know? Before there was an internet, the world was one way. After there was the internet, the world is a new way. We're experiencing that now. But let's understand what these models are made of. The great transition happened because of, basically we got on this journey because of a particular style of AI. And it's a class of AI that folks will refer to as deep learning, where we're mimicking the functionality of a brain, right? We discovered in neuroscience that neurons can learn anything. And based on that, computer scientists figured, well, the way we can have computers mimic intelligence or cultivate intelligence could be by mimicking the brain. So here I have a picture of a very, very groundbreaking experiment where the research questions was, can we have arbitrary neurons that were never evolved to solve a task, solve a new task, learn a new task it wasn't able to solve? So they put a pigeon in a Skinner box, and they asked they trained the pigeon. They attempted to reward the pigeon when it can make a distinction between 2 artists, Van Gogh and Chagall. And so the pigeon would look at, say, Van Gogh, and it'll tap a particular spot to recognize the creator, and the results were phenomenal. Like the pigeons were able to 95% of the time, when seeing a painting, identify whether it was Van Gogh or Chagall. And indeed, 85% of the time, if it hasn't ever seen a painting from that particular artist, it was able to make that distinction. This is a very important moment. At this moment, it was proven that neurons can learn pretty much anything, right? Things that it wasn't evolved to learn. And so based on a wealth of that studies, of course, what does the computer scientists do, right? The computer scientists have been working on trying to get computers to mimic human intelligence. You know, they use logical symbolic means. They came up with regression models and statistical systems and all of these things. And then there was a class of this investigation that asked, well, can we simulate what actually happens in biology? Can we simulate the neuron? And neurons are understandable, right? So in a neural network, and this is what these models are made of. This is what ChatGPT is made of. Is
Jason, sorry, you got muted.
Oh. Okay. Oh no. Is that better?
It's
Can
just
you hear?
5 seconds ago. 5 seconds ago.
5 seconds ago. Oh, yeah. So just to recap 5 seconds worth of what I was talking about. Yeah, so neurons are connected, right? And it turns out that the functionality of a neuron has to do with its likeliness to send an electrical signal out, right? So it relieves electrical signals through, we can refer to as inputs, right? Through synapses, and then it will cascade that electrical pulse out. Very, very easy system to simulate, right? You can simulate it with inputs that are numbers between 0 and 1. 0 being there's no signal, right, from that particular input. 1 being I have the strongest signal from that input. And you can have a number of these inputs that are listening to signals, you can think of it. And then the neuron has something called an activation where it's going to output a signal based upon the inputs that come in. So very, very, very simple to simulate. And the way we do that is we have neurons, which are the nodes in this graph, and then you have synapses, which are the weights. So the weights are on the edges of this graph. This is a simple neural network. This is called an artificial neural network. The difference between a deep neural network, and it's important that saying that you've taken this class, this is terminology you need to understand, right? The difference between a deep neural network and just a regular neural network, an artificial neural network, is the number of hidden layers, right? So these nodes are organized in a way where, let me just get my annotation going here. Hold on. This interface has changed. Let's see. There we go. So, so we have a hidden layer. We have a layer that we only have one layer in this network. If you have multiple layers in the neural network, it's called a deep neural network. Now, the signals that come in are the inputs to a neural network, and then the signals that go out are the outputs, right? So we'll look a little bit deeper as to what comprises a neuron. Okay, so the structure of a neuron is such that there's a set of inputs, what we call a squash, and then a particular signal out, right? And that squash is performed, there's an activation function that'll determine the strength of that output based upon the strength of the input. So if all of your inputs sum to be, say, 4.7 in this case, based on the activation function, you'll have an output out of that model. And this simulates exactly how our neurons actually work, right? So you've got an axon between two neurons. These are the nodes. And then the synapse is the connection between your axon and the dendrites, the inputs to the other node. And we're essentially mimicking that electrical signal with a weight between two neurons. So we'll look at what these inputs are, and then we'll talk about what outputs look like. Here's an example. The outputs could be distinguishing the difference between Batman and Superman, right? So this might be the likeliness that it's Batman. This might be the likeliness that it's Superman. And you can have a number between 0 and 1 for that likeliness. So if this says 0.9 Superman, 0.1 Batman, this neuron would be making a prediction that in the picture, and the picture would be the pixels that came into the neuron, is it Batman? Is it Superman? And that determination is made based upon the weights and the neural networks and the activations in that network. And we'll talk about how learning works in a bit. And so it's quite simple, right? So we use something called a sigmoid, and I'm not going to go too much deeper into this, because once you understand what a neuron is, then we can quickly pop up to understand, well, how does that relate to what ChatGPT is, right? And so, so if you have inputs, say 1 and 0.5, right? This could be the strength of pixels, and we're gonna describe a more relatable example soon. The weights are coefficients that'll change the strength that will be the input to the next neuron. And we use an activation function that determines how we modulate that strength of input. The beautiful thing about this, the beautiful thing about this is all we're using to solve a task are the strength of inputs, right? So we'll look at an example of what the inputs look like, but on the outputs, an electrical pulse of 0 would be with no electric pulse would be 0, and the strongest electrical pulse would be 1. And you can associate those outputs to things that have meaning, such as Superman versus Batman, for a neural network that's predicting a picture. So the key question is, how do you configure these weights such that it can tell? And so we're going to talk about that with a concrete example, and it's one of my favorites. It's called MNIST. So when we refer to inference, inference is the process of looking at inputs and making a prediction. And inference is distinct from training. So we're going to talk about what training means and what inference means, right? So assuming that this neural network has learned how to recognize digits, right? So this is a classical neural network. It's called MNIST. And if I'm going too fast, feel free to ask questions in the chat. But this is a neural network called MNIST, right? And as we talked about before, we have neurons and we have weights, right? These weights, these inputs to this neuron will sum up to be the strength of signals in, and then we're going to have an electrical pulse out, and it goes out to all the neurons. And that electrical pulse, and let's call it a value between 0 and 1, is going to determine the inputs to the next neuron until we ultimately have an electrical signal pulse out on the output layer. Now, this particular output has 10 nodes, and each node represents a particular number, right? So this is a digit recognition model. And so it'll look at a picture, and we'll talk about that in a second. And then it'll tell you, it'll give you an electrical signal through each of these neurons as to its prediction as to what value is in the picture. Now, when we look at this picture, how do we get this picture into this input? Well, it turns out that each one of these nodes, there's 784 of said nodes, right? There also is 784 pixels in this image. And this is a grayscale image. So what that means is black, you can represent with 0. And white, perfectly white, you can represent with 1. And then any value in between is gray. And so the inputs here are associated with each of the pixels that come in. So it's only seeing electrical pulses, right? In, and it only produces an electrical pulse out. I'm using this electrical pulse to be a value between 0 and 1. It's all math, right? This is a mathematical model. A neural network is a mathematical model that is mimicking how neurons actually work and learn in our brain. So when it sees an image, let's assume that this model has already learned, and we're going to talk about what learning is in just a second. When it sees this image, the highest pulse will be 5. It'll be 0.8. A value of 0.8 will come out here. And then all of these will be like 0.1, 0.1, or some 0.02, 0.02, 0.02, right? And then 0.9, 0.8, and then 0.02, 0.02, right? And so that's the functionality of an inference of an already trained model. Is there any questions on that? Does that make sense? Does it make sense how you can set up this simple, you can create a neural network out of these neurons, this mathematical simulation, to then be able to solve a problem, like on the inference, right? Because all you need to do in this model is go from 784 nodes in, use the weights, which modulate, these weights modulate the values as the values cascade, and then those values are reduced to 10 values, and each of those 10 values correspond to a particular number that's being predicted. Now, the big question is, okay, well, how does that happen? How do these weights produce the right pulse on the output? Well, that comes from learning. Now, the process of learning, there's a notion of neural capacity, right? It's the capacity of these weights. How much can they learn? What can they learn? Well, it turns out this particular model has enough of these weights, these lines, such that you can identify a set of coefficients for the values that are coming in, such that the particular configuration of those coefficients will give you the right answer. It sounds like magic. It's because it kind of is. The way that we actually come up with that, let's assume there is a configuration of values for these lines such that when you get these pixels in, it'll just give you 5 out. Well, how do you find those values? Well, it's a search. It's a random search. It's called stochastic gradient descent. Stochastic in that means random, right? Gradient descent refers to you're updating the weights with a gradient as you go back into the model, right? It's a random search. So it's a numerical optimization fundamentally. We're randomly looking for the right configuration of nodes of weights such that this model can make good predictions. The fascinating thing is this model actually does better than humans at recognizing digits. And that's the process. So how do we find those weights? Well, we find those weights using training the model, right? So all of these models, when it comes in, the initial version of the model is random, right? So the model just makes random pulses. These weights are random values between 0 and 1, let's say, right? It's just random. So the model is really, really not smart, right? It's like a baby that doesn't understand anything about the world, and then you start giving it examples, right? And those examples allow us to search for the right weights. So how could that work? Well, in training mode, when it starts with no information and it can't make a prediction, you give it a training set, right? You give it pictures and the right answer, right? So it's similar to Batman, Superman. It's like, here's a picture of Superman. I'm going to tell you this is Superman. Then the weights are going to be updated to be Superman, right? So you give it examples until it gets really good, right? So you say, hey, this is a 1. I'm going to reconfigure your weights until you would have predicted 1 with these pulses, right? So I'm going to show you a set of pulses, values between 0 and 1 for each of these pixels. And then I'm going to tell you, you need to predict 100% 1, 0% for everything. So I'm going to search for those weights such that I'm going to change all of the weight values such that 1 is what pulses the strongest and everything else is really low when I show you a 1 and tell you the answer. So this is training. It's labeled data, right? And then after the model is trained, then it can see new examples and be able to do the prediction out, right? So we've got our model, we train it first, and then that trained model is deployed to the market. Now, I mentioned, and I'll go through this part a little faster. Well, you can dig into this stuff. ChatGPT is there. Feel free to chat with ChatGPT to go deep. And there's a wealth of information to discover about the landscape of this. But just to link it back to the era that we're seeing right now, this is the search, this is the random search, and we have this notion of a loss, right? So you can actually tell how off the prediction is, how wrong it is, and then take advantage of that value to drive that search. So you can get there quickly, right? That's the stochastic gradient descent with a loss function. So what does a loss function look like? So essentially, if you give it a 1, and then it makes a prediction out of these, you have 10 numbers out, you can actually calculate the difference between the value that you want it to be. And then you can take advantage of that loss. How off was it? Perhaps you give it a 1 and it says 0.5, and then everything else is like 0.1, 0.1. So it might get the right answer, but it could be more right if it was 0.9 instead of 0.5. So that would be a 0.4 loss. And then you can use that 0.4, you were only 0.4 off to determine how much you randomize the weights. Now, to link this back to the era that we're in today, there's an important thing that we discovered, right? It turns out that this is laborious because you have to label all the examples. You know what I mean? You have to have that training set. And humans usually are the gold standard to that training set. So you have a whole bunch of humans look at numbers and label it. And then that's the training set, and you have to grow the training set until the model learns enough, and then you need more examples based on the size of the model. So that was really, really hard. Models couldn't learn themselves. They had to be trained. And then a big innovation happened, right? And that innovation is we discovered an interesting way for these models to train themselves. And so we call that self-supervision, right? It used to be called unsupervised, but then the language got tuned because it's not unsupervised. You're still determining the environment you want the model to learn in. It's self-supervised. The model learns on its own. So this is another exactly the same neural network as we looked at before. It's just drawn a little bit differently, but these are input layers, and these are all neurons, right? And then you have a hidden layer. These are neurons. And then you have an output layer. These are neurons, right? These are neurons, right? So this is just the same thing drawn differently. Now, the cool thing is we talked about how easy it is to turn a pixel into an input to the neuron, a number between 0 and 1. You can also do that with words, right? I'm not going to get into the details, one-hot encodings and all that stuff, right? I mean, I teach a whole class on this, on just this stuff, on just this little piece. So we're really taking a very intuitive, high-level view, detailed view at a high level through all this stuff, right? So given an approach to convert a word into neuron inputs, pulses, which we can do, it's one-hot encoding and various embeddings, so you can chat GPT that later. This works exactly like MNIST, basically. But the cool thing is, the problem isn't give me a classification of like 10 things, right? Which is the previous model. The problem that this model is set to solve is, I'm going to show you, it's fill in the blank, right? So if all the model has is the context words, I natural, tell me the missing word in the middle. I'm only talking about CBOW. Skipgram does the opposite. Skipgram, you just give it like, and then it's like, tell me the words around it, right? Make a prediction as to the words around it. So that's Skipgram, but let's only talk about CBOW because it's more intuitive. And it also is relevant here. So if you have a task, if you set up a task, and this is called a pre-training task, right? This is your self-supervised task. You'll often hear terms like pre-trained model versus fine-tuning the model. So I'll give you an example. If you're familiar with generative AI, you would hear, oh, Facebook just released Llama 3. Llama 3 is coming out, actually. Facebook is releasing Llama 3, the greatest pre-trained model on the planet. And then, oh, I'm going to fine-tune Llama 3 to do X, Y, and Z. All that means is it's a difference in task, right? So a pre-training task, like fill in the blank, is a task where it'll learn about the world, right? It's just go learn, self-supervise yourself, fill in the blank. And then you can fine-tune it with, now I want you, now that you're really smart, I really want you to focus on one problem, right? Okay, so this pre-training task is fill in the blank as you scan through words. And what was discovered is if you take a model like this and you let it read Wikipedia, the model learns more than how to fill in the missing word. This was the big transition that kind of got us on a unstoppable train to ChatGPT, right? It's like, okay, self-supervised, we don't have to label data. I don't have to look at every combination of two words in Wikipedia and then have a human specify the missing word was like, the missing word was natural, the missing word was language. The model can just do that. It's inside of the Wikipedia itself. And what we discovered is you can take a model like this and train it such that the model learns more about the world. So it's doing a simple task. And this is how all this stuff works. It's wild. I mean, ChatGPT and GPT-4, its pre-training task is predict the next word. This is predict the missing word in the middle, right? These GPTs that we're using now had a simpler task. Predict the next word. Oh, I saw the cat jumped. What's the next word? Predict it. Over. What's the next word? Predict it. The over fence, right? Predict the next word. That's actually how you pre-train all of those other models, right? Like the models we use today. This one is predict the word in the middle. But this particular moment was the discovery that got us to realize that these models learn more about the world than the task. One of the most special discoveries was concepts like if you can use the representations the model has for the word to do math like king minus man plus woman equals queen, right? So that means that in that model, after the model learned, where is it? Oh, after the model learned to predict the missing word, it also happened to learn that a queen is essentially a king, but a woman instead of a man. That's a queen. The model learned that. So that means this was a happy accident too. That means that, when you let these models self-supervise and learn on their own, let's say with text, let's say with Wikipedia or the internet, these models become really, really, they learn more. So then we just went further. Like, how do we make the models bigger? How do we change the task? You know, the transformer neural network was created by Google. And this is a big model that was created to be more trainable, more parallelly than sequence to sequence models, recurrent neural networks. It's a long story, but we created the transformer to take advantage of this pre-training, and that was huge. There was this thing called BERT. Everybody was crazy about BERT. Oh, BERT's even smarter than this word to vec model. And so we kept going until we discovered a technique that allows us to take these pre-trained models and have them automatically fine-tune themselves, right? So we can have two models fighting each other. You can have one model challenge the other to do better, and then It can even train themselves by bouting, by fighting, right? And so that's essentially what gave us the ChatGPT revelation, but it really all just comes back to this simple insight. Self-supervision allows models to learn generally about the world. And that got us to where we are today. Then everyone spent billions of dollars to captivate this technology. There's hilarious stories of Google, like immediately after ChatGPT came out, Google had a press conference, and then they were like, we invented the transformer, guys. We have better tech than that. It was so hilarious. I mean, the level of flailing that happened from Google. And indeed, Google did invent the technology that OpenAI was able to wield to create the iPhone moment. And so now we're in a crazy fight. Since ChatGPT, Microsoft is now the #1 market cap company in the world. It wasn't before November 2022, right? It was like number 3. And so how correlated are these? I think they're pretty correlated, right? Microsoft has been very savvy. In the AI game, Microsoft very savvy, and in the gaming market, Microsoft has been very savvy. They're just dominating. It's crazy. Anyway, but so there was a thesis that only the big companies would have it, and it turns out that since this moment, everyone's trying to have it, right? And there's been this sprint towards making things smaller, more creating tool sets to build with this technology, understanding what it means for product development. Indeed, you'd be surprised how much activity is happening around this technology and how few folks are actually putting it into products everywhere. Like it's both happening incredibly fast and incredibly slow, right? If you go to let me give you an example. If you go to an app store today, there's still a whole bunch of apps that aren't necessarily wielding this technology, but everyone's trying to figure out how to do it. And this is exactly what Giseki Labs is focused on, right? So you guys have seen and perhaps heard of the incubation center that we've started in Sri Lanka, BCS and Giseki Labs, right? I mean, the story behind this is a story I'll probably tell in some lecture, but it's a wonderful story of creating the means to have impact in the world, taking the minds of Sri Lanka, which are just brilliant. There's the rich level of brilliance to be able to have impact in a way that's democratized across the world. And so Giseki Labs is focused on this, and our mission is to create and invent the technologies that advance how we code, innovate, and live in this generative AI era. So we're with fervor creating open source technologies that is available to everyone. We're sharing everything we discover along the way. We're publishing, we're creating, and we're incubating the methodologies and capabilities that will determine what is possible when it comes to the products of the future with this technology, right? We do engineering, we do research, we do advanced development, right? And so essentially, as part of this seminar, you guys are going to be able to engage with the incubation center. And folks in the incubation center is going to participate in guiding and leading you guys through the journey. Today's class was really about some background knowledge, terminology, understanding really what these things are, because when we look at the papers, it's going to be very important to kind of have some of that context, right? And then after the papers, we're going to be using some tools. We're going to be tinkering with some technologies, and you'll have an opportunity to contribute to the art of the possible with us. And so you'll get to know us very well on this journey. I think the grand challenges that we're going to be focused on in this class is how do we program in this new era? Look, one of the biggest things that's going on right now is systems like LangChain, agents, memory. you guys are going to learn about a number of these technologies that Llama Index, like how do we actually get our programs to take advantage of this Gen AI to solve great problems? Guess what? In Jaceki Labs, we're inventing the next generation of such technologies. Right now, we're kind of code word calling it MTLLM, which is meaning typed large language models. And so we're going to write a short paper on that one soon and share it with you guys. But we're working on the next generation of that. How do we program? How do we get the LLMs to do what we want? How do we create the right fine-tuning and prompt training systems to get these models to be very good at specific tasks that we want and that anyone wants? How can you run it on your laptop? How do we gain control of these LLMs so that it can run in your phone, run on your laptop? You can wield it and you can build incredible experiences out of it. And so this is kind of what we're working on. And we actually have one of such contribution. We've actually published in like record time. I mean, if you guys have been following the work that University of Moratuwa has been doing, I've been doing in collaboration with Moratuwa, Jaceki Labs has been contributing to the world. Like if you've been following it, you know the incubation lab started like yesterday. And already we've published a top tier paper that's going to be presented on the 5th of May that tackles a very important open question. So we've gotten a quick win already with the lab, and it's a collaboration between folks that are connected to the lab, folks at University of Michigan, et cetera. And we've gotten we did an interesting study. The study looked at the generation of open source small language models versus the behemoths of, say, ChatGPT. So that's why we have this little, this is a housefly, and then this is GPT-4. This is the blue whale. This is the largest mammal on the planet Earth. It's like, I don't even know the statistics. It's like, I don't know, like 1,000 cars big or something, right? It's massive. And then this is a housefly. And so it turns out that models that are 200 times smaller are able to do just as good as ChatGPT. And so we did a rigorous study of the implications of that, right? And you guys, I'll refer you guys to the study, and you guys will end up reading this as you know in this class. But yeah, anyway, so this is really the landscape of the work that we're going to be doing in the Innovation Center. There's all innovation in computer science happens across this stack, right? This is the art of everything that's been possible goes through this stack, from applications to algorithms. This is where all the machine learning, deep learning stuff happened. Essentially, ChatGPT is an application, right? Like it's actually a fine-tuned version of these things. There's programming languages, there's lower machine code, there's the architecture, the processors themselves. This whole stack is an AI stack. And the biggest companies in the market are like NVIDIA, which make processors. And NVIDIA is eating the lunch of Intel and AMD. So we care about problems across the stack that's relevant to the future. And a particular area has stagnated. And we're experiencing that today with the creation of things like LangChain and so forth. And that is, how do we wield these models to solve problems and build products and software? And so this is, I think, the hottest problem space to solve moving forward. So we're going to look at that problem space in detail. We're going to look at cross-layer solutions, vertical integration, co-design. These are kind of the themes as to how to have impact these days. So we're going to look at some of that. And we're going to understand this ecosystem of open source technologies that's enabled the creation of many products and companies that were created by teams you wouldn't expect to be able to create AI. So we're going to be looking at all of these things in the scope of the class. And with that, as an introduction, as an overview, we're going to get into nitty-gritties next time. And we're going to get everybody connected to that forum online later today. And so with that, I'm happy to open it up for any questions or comments or thoughts. Yeah, feel free to ask in the chat. Yeah. So we had a question earlier. I just joined the lecture. Will a recorded video be shared with us after the session? Yeah, I'm sure. So this is recorded. And Loggy can share more.
Yeah, I answered that question, Jason, already.
Sorry. Sorry. Yeah, good. Any other questions from anyone? Don't be shy, like, you know. All right. Well, oh wait, there's one. What are your thoughts on Moravec paradox and application of AI to robotics? So I'll talk about I'm not familiar with the Moravec paradox. Let's take a quick look. But I will talk about AI and robotics. Observation of artificial intelligence. It's the observation, and let's look at it together. The Moravec paradox is why is this happening? Oh, I still have it on annotate. Let's do this. Okay. The Moravec paradox is observation in artificial intelligence robotic. Contrary to traditional assumption, reasoning requires very little computation, but sensory motor and perception skills require enormous computational resources. The principle articulated, blah. Okay, so I'll talk about this after, but what I'll say about AI and robotics is all of the technologies we've invented has come from a deep desire to reproduce ourselves. Like even computers, right? We want to increase productivity. We want to increase leisure. So we create these tools, and we've been marching towards more personalized intelligence, right? We want not a computer that's stuck at home. We want to be able to take it with us on the go in a laptop. So we want that laptop so we can take it anywhere. Oh, we want it in a smartphone. So now we're all on our smartphones. We want it to have more information on us. We want it to be an external brain, right? Where we can record everything. And then we're fascinated with AI, and we want it to be as intelligent like another human. I think robotics is an important and a must happen step in the human journey, in the human species journey. I don't think we've had our iPhone moment yet. So it's really important to understand there are these moments that you can record in history where everything changed. Industrial revolution, everything changed. Television, everything changed. Like society changed, media changed. The internet, right? The computer itself, the smartphone, everything's different. Now everybody's on TikTok. You know what I mean? Like everything changes with these moments. And before each one of those moments, there was the same technology preamble to that moment, right? Even the iPhone had Palm Pilot, Blackberries. It was a niche, and then it became ubiquitous, right? So we go through these cycles of niche and ubiquitous. Robotic is still niche. I think we're actually marching toward that moment when we have an iPhone moment with the robot. I think there's a wonderful space of recreational AI that people don't really work. Everybody's focused on productivity, but a robot pet with a GPT in its head, that's a product I would buy. Startup idea, let's build that. You know what I mean? So I think it's inevitable. Because it really just comes from an inner human desire. The Moravec paradox, I think what this is referring to, I'll have to read it more deeply, seems to refer to the idea that much of our neural energy expenditure isn't to think the deep, hard questions, but it's sensing, it's like moving, it's ganglia, and so forth. One thing I'll say to that is when you think about neural networks and the way we simulate it in computers, think about that as analogous to the way an airplane simulates a bird. There are some aspects of the airplane's design that takes advantage of the aerodynamics that biology has created for birds, right? Like there's wingspan, there's like wing to body ratios, weight stuff. However, the plane doesn't flap its wings. And every bird flaps its wings. And it actually would be inefficient for us to try to build machines that flaps its wings. And so when you see AI mimic biology, there's some aspects of the biology that is being mimicked with the neural network simulation that happens in computers, but it's not the full, it's not like every good idea that biology produced we should replicate, right? Think about neurotransmitters like dopamine and serotonin and epinephrine and all these different hormones that actually modulate our ability to think and our activities, testosterone, the activities we do, like aggression, like all that stuff. We don't do that in models. We don't mimic that either. So I think we'll always see that distinction. I don't think we'll ever see a plane that flaps its wings. And I also don't think we'll ever see a model of the human biology that is completely congruent. I'm interested in Giuseppe project and want to contribute more. How do I do this? Connect, right? So get on the piazza and reach out. Basically, if you email me, I'm happy to stitch you in. Talk to Loggy. Loggy is the connective tissue to everything that I have going on right now, and it keeps growing. It's crazy. Like Loggy is my I don't know. Anyway, so Talagi is a good person to talk to. What do you think about SOCs and embedded with neural networks like stuffs, Apple A series like? How do I study about that? And please explain a rough roadmap. SOCs and embedded with neural networks. I think that the roadmap for neural networks living in embedded systems is really a hardware bottleneck. And it's going to come from, I'll tell you exactly. I have a prediction of what's going to happen. What's going to happen is now that the technology is ubiquitous, there's going to become a model that will last for a very long time. A neural network architecture, fundamentally, it might be the transformer. And then we're going to accelerate it to kingdom come with ASIC technology. We're going to create a new kind of processor that's highly energy efficient for said model. And we'll start fabbing those. And then when we have that, and when we master, we've just discovered what this paper talks about. We've just discovered some of the properties and attributes of what happens if we make models smaller. How do we make models smaller? This research has lit up on fire, quantizing models, fine-tuning models, getting models to be one megabyte, like 1 gigabyte instead of 10,000, 10,000 gigabytes, right? Like, how do we do that, and how do we retain intelligence? So models are going to get small, hardware is going to start accelerating it, and we're going to have more specialized hardware for neural network inference. And then we're going to see that landscape of what's possible with connected devices or embedded devices expand. Right now, the best thesis is you use the device as sensing, and then it's a connected device to the cloud. And the real heavy-duty AI has to be run in a data center. I think that's going to change. Do you think AI will replace programming and the need of learning programming languages? This is a very good question. And I believe that there's this unfortunate thing happening right now where we have a generation that is getting the advice, don't study computer science and technology because the AI will do it. Like, that's getting in the air, and it's the most tragic thing ever. Because at the end of the day, guys, this is a tool, right? It's a tool that helps you do more and do more faster. And there's a foundational core, durable reason why the AI will never replace that kind of work. The reason is humans will always hold other humans accountable, right? Imagine if I had an AI that wrote the software for my company. My company creates an app. I have an AI that just does it. No human. There's a bug in the software. I need to get mad at somebody for that bug. I don't want to go to an AI and say, I'm so mad at you, AI. Like, you need to fix this right now. We're going to always want a human to be accountable and responsible for what a company outputs. That's fact number one. So be that human. We're going to need a lot of them because this technology is going to be everything that's driving our economy. So we're going to need a lot of humans that know how to program, create, control this AI, but we're going to have to learn how to live in a world where we have to control that AI. Reason number two, everyone says, oh, well, we're going to lose jobs. That's not how the world works. If my business can afford 10 employees, and then my AI can make each employee 10x more productive. One might think, oh, I'm going to fire 9 because now with the AI, I don't need 10, I just need 1. And I can do the same output. But that's not how the world works. If I can do 10x more productivity, I'm just going to do 10x more productivity. I'm going to keep my 10 engineers, and then I'm going to have 100x productivity, right? Or I'll have 10x productivity overall for the whole company. I'll just increase my revenue 10x. I'm going to turn that productivity advantage not to keep my same level of output. I'm going to increase my level of output because now engineers are just 10x more productive. And that's the reality. And the truth of the matter is, what you'll find out is, let's say this generation just studies, I don't know, to be doctors. There's going to be a scarcity of folks, and those folks are going to get paid very well. But at the end of the day, I think it's a big and unfortunate message that we're giving young people to, oh, well, AI is going to replace that job, so don't work on it. It's complete nonsense. Anyway, cool. Any other questions? Awesome. All right, I'll hand it over to Lagi. Thanks, guys, so
Okay.
much, and I'll see you next week. Yeah.
Yeah. Thank you, Prof. Jason, for the wonderful seminar as usual. So we will also meet every week Thursday, actually 6:30 p.m. to whenever it goes. So everyone likes to learn AI a lot. The time doesn't limit. So let's meet next Thursday. Thank you very much, Jason.
Yep.
And
Thank you, guys.
thank you everyone for joining.
Awesome. Thank you, guys. Talk soon. Yep. Later. Yep. Bye.